You are not where you think you are. Neither is Earth, neither is the Sun, neither is the entire Milky Way galaxy. For centuries, we believed we understood our cosmic address. We knew Earth orbited the Sun. We knew the Sun was one star among hundreds of billions in our galaxy. We even knew our galaxy was part of something bigger, a cluster, a supercluster, a neighborhood of galaxies. But we were wrong about the neighborhood. Spectacularly wrong. It wasn't until September 2014 that astronomers finally discovered where we actually live. And when they did, they had to create an entirely new map, because the old one was missing almost everything. Here's the part that will make you question everything you thought you knew about space. The universe isn't a random scatter of galaxies floating in an endless void. It has a structure, an architecture, a design so vast and so intricate that it took us until the 21st century to even begin seeing it. Imagine a spider's web stretching across 93 billion light-years. Now imagine that web is three-dimensional, with threads and intersections and vast empty spaces between the strands. Galaxies aren't randomly distributed. They're arranged along those threads, clustering at the intersections, avoiding the voids in between. This is the cosmic web, and you're part of it. Right now, as you listen to this, Earth is moving through space at over 2.1 million kilometers per hour, not just orbiting the Sun, not just orbiting the galaxy, but being pulled toward a point in space we couldn't even see until recently. Every galaxy in our neighborhood is flowing toward the same destination, like rivers converging on a single valley. Something is pulling us, something massive, something we can't fully explain, and that's just the beginning. In 2013, astronomers discovered what may be the largest structure in the observable universe, a wall of galaxies so enormous that it shouldn't be able to exist according to our current understanding of physics. It stretches across 10 billion light-years. That's more than 1/10 of the entire observable universe. If this structure is real, it challenges the very foundations of cosmology. How did we miss all of this? How can something 10 billion light-years across hide from our telescopes? And what does it mean that the universe has a structure at all? That it's not chaos, but a pattern? Today, we're going on a journey. We're going to travel from Earth outward, scaling up through every level of cosmic organization. We'll discover our true address in the universe. We'll see the filaments and voids that shape where galaxies form and where they don't. We'll encounter structures so large they strain the boundaries of known physics. And we'll confront a profound truth, that our position in this cosmic web isn't random. It's the reason we exist at all. Let's find out where we actually are. Start with what you know. You're on Earth, a rocky planet orbiting a medium-sized yellow star we call the Sun. Earth moves through space at about 107,000 kilometers per hour, completing one full orbit every 365 days. You've known this since childhood, but here's where it starts getting interesting. The Sun isn't standing still. Our entire solar system, the Sun, all 8 planets, moons, asteroids, comets, everything is racing around the center of the Milky Way galaxy at 828,000 kilometers per hour. At that speed, you could travel from New York to Los Angeles in about 17 seconds. Even at that incredible velocity, it takes the Sun 230 million years to complete a single orbit around the galaxy. Astronomers call this a galactic year. So, Earth orbits the Sun, and the Sun orbits the galactic center. That's 2 motions happening simultaneously. But we're not done. The Milky Way itself isn't stationary. Our galaxy is one member of a family called the local group. More than 50 galaxies gravitationally bound together, all moving as a unit through space. The 2 biggest members are the Milky Way and the Andromeda galaxy. Between them, they dominate the local group. with dozens of smaller dwarf galaxies orbiting around them like satellites. Andromeda is about 2.5 million light-years away. It looks like a faint smudge in the night sky. If you know where to look, you can see it with your naked eye. What you can't see is that Andromeda is rushing toward us at 400,000 kilometers per hour. In about 4.5 billion years, the Milky Way and Andromeda may collide, though recent 2025 research suggests there is roughly a 50-50 chance the collision might not happen at all, due to the gravitational influence of the Large Magellanic Cloud. If they do collide, it will not be like cars in an accident. There is so much empty space between stars that very few actual stellar collisions will occur. Instead, the galaxies would pass through each other, get pulled back by gravity, pass through again, and eventually merge into a single giant elliptical galaxy. Astronomers have already named this hypothetical merged galaxy Milky Way. But we're still scaling up. The local group is part of something larger, the Virgo supercluster. This structure contains about 100 galaxy groups and clusters, all loosely bound by gravity, spanning roughly 110 million light-years. At the center sits the Virgo cluster, a massive collection of over 1,300 galaxies. If the local group is a small town, the Virgo cluster is a major metropolitan area. Our little family of more than 50 known galaxies is located on the outskirts, in the suburbs of this cosmic city. For decades, astronomers believed the Virgo supercluster was our ultimate cosmic home, the largest structure we belonged to. Textbooks were written, maps were drawn. Students memorized the hierarchy: Earth, solar system, Milky Way, local group, Virgo supercluster. They were all wrong. In 2014, a team led by astronomer Brent Tully of the University of Hawaii made an announcement that rewrote our cosmic address. Using a revolutionary new mapping technique, they discovered that the Virgo supercluster isn't an independent structure at all. It's just one small corner of something much, much larger. Everything we just described, the local group, the Virgo cluster, structures spanning hundreds of millions of light-years, turns out to be a single lobe of a supercluster so vast that it needed a new name to describe it. They called it Laniakea. For decades, astronomers faced a frustrating problem. Superclusters, those immense collections of galaxy clusters, had fuzzy boundaries. Where does one end and another begin? If two groups of galaxies are near each other, how do you know if they're part of the same structure or just neighbors that happen to be close? Traditional mapping techniques showed you where galaxies were, but not how they related to each other. It was like trying to understand a city's traffic patterns by looking at a still photograph. You could see where the cars were parked, but you couldn't tell which way traffic was flowing. Brent Tully and his team tried something different. Instead of just measuring where galaxies were located, they measured how they were moving. Every galaxy has two types of motion: the expansion of the universe pushing it away from us, and its own local motion caused by gravitational attraction to nearby mass. Astronomers call this second type peculiar velocity. By mapping the peculiar velocities of over 8,000 galaxies, Tully's team could see the gravitational landscape of our cosmic neighborhood. They could trace where matter was pulling galaxies toward it and where it was letting them drift away. Think of it like mapping watersheds on Earth. If you pour water on a continent, it flows downhill toward the nearest ocean. The continental divide determines which water goes east and which goes west. You could map these watersheds by tracking which direction water flows at every point. That's essentially what Tully's team did with galaxies. They mapped the cosmic watersheds, regions where galaxies flow toward the same gravitational center. And what they found was extraordinary. There's a gravitational valley in our corner of the universe. Everything within 500 million light-years is flowing toward the same point, the bottom of that valley. This includes the Virgo supercluster, the Hydra Centaurus supercluster, and several other structures that astronomers had previously considered separate entities. They're not separate. They're all part of the same supercluster. They're all being pulled toward the same gravitational center. Tully's team named this newly discovered supercluster Laniakea. The word comes from Hawaiian, Lani meaning heaven, and Akea meaning immense or spacious. Immense heaven. The name is fitting. Laniakea spans roughly 400 to 520 million light-years across, depending on how boundaries are measured. It contains approximately 100,000 galaxies. Its total mass is about 10 to the power of 17 solar masses. That's 100 million billion times the mass of our Sun. If you could see it from outside, it would look like an enormous cloud of galaxies, all slowly streaming toward a common center. And that center has a name too. It's called the Great Attractor. The Great Attractor was discovered in the 1980s, long before Laniakea was identified. Astronomers noticed that our galaxy, along with everything in our neighborhood, was being pulled toward a specific point in the direction of the constellations Centaurus and Norma. Something massive was tugging at us. The problem was, we couldn't see it. The Great Attractor lies behind the densest part of our own Milky Way, hidden by all the dust and stars in between. We could measure its gravitational effect, but we couldn't photograph it. For years, the Great Attractor was one of astronomy's greatest mysteries. What could be massive enough to pull entire superclusters toward it? Tully's 2014 discovery provided the answer. The Great Attractor isn't a single object. It's not some supermassive black hole or mysterious cosmic anomaly. It's simply the gravitational center of Laniakea, the lowest point in our cosmic valley. Just as water naturally flows to the lowest point in a landscape, galaxies naturally drift toward the densest concentration of mass in their region. The Great Attractor is where all those streams converge, and we're part of the flow. Right now, our entire local group, including the Milky Way, Andromeda, and all the galaxies in our family, is moving toward the Great Attractor at about 600 kilometers per second. That's on top of all our other motions. Earth around the Sun around the galaxy through the local group. Add it all up, and Earth is moving through space at roughly 2.1 million kilometers per hour, carried along by the gravitational current toward the heart of Laniakea. We have finally established the contours that define the supercluster of galaxies we can call home, Tully said when announcing the discovery. This is not unlike finding out for the first time that your hometown is actually part of a much larger country that borders other nations. But here's what makes this story even more remarkable. Laniakea, as vast as it is, isn't gravitationally bound. Unlike a galaxy cluster which is held together by gravity, Laniakea is too spread out to resist the expansion of the universe. Over billions of years, dark energy, the mysterious force accelerating cosmic expansion, will tear Laniakea apart. The supercluster we call home is temporary. It's a pattern in the flow of matter, not a permanent structure. The galaxies flowing toward the Great Attractor today will eventually be scattered by the expansion of space itself. We exist in a brief moment when Laniakea is visible and coherent. And there's one more twist. Laniakea isn't the final level. We're not just being pulled toward the Great Attractor. Laniakea itself is being pulled toward something bigger. The Shapley concentration, a supercluster 10 times the volume of Laniakea, which may itself be part of an even larger basin of attraction. the cosmic address keeps getting longer. Now that you know your address within Laniakea, let's zoom out and see the bigger picture. If you could somehow travel outside the universe and look back at all of it at once, all 93 billion light-years of the observable universe, what would you see? Not a random scatter of galaxies, not a uniform glow of light. You'd see a web. The cosmic web is the largest structural pattern in the known universe. It's a three-dimensional network of matter that stretches across the entire observable cosmos, connecting everything to everything else through an intricate lattice of threads and intersections and empty spaces. Imagine a sponge. Not a neat, uniform kitchen sponge, but a natural sea sponge with irregular holes and channels running through it. The material of the sponge represents where the galaxies are. The holes represent the voids, regions almost empty of matter. The channels represent the filaments, long strings of galaxies connecting dense regions. That's roughly what the cosmic web looks like. Scientists divide the cosmic web into 4 types of structures: nodes, filaments, walls, and voids. Understanding each of these is key to understanding where galaxies form, how they evolve, and why the universe looks the way it does. Let's start with the nodes. Nodes are the intersections of the cosmic web, the points where multiple filaments meet. These are the densest regions of the universe, containing massive galaxy clusters with hundreds or thousands of member galaxies. The Coma cluster, the Perseus cluster, the Virgo cluster, these are all nodes in the cosmic web. At a node, gravity has pulled together an enormous concentration of matter over billions of years. The galaxies within these clusters are packed relatively close together, influencing each other through gravitational interactions, stripping gas from each other, merging, and generally creating chaotic environments where star formation eventually shuts down. If you're a galaxy born in a node, your life will be eventful but probably short-lived in terms of active star formation. Next are the filaments. Filaments are the threads of the cosmic web, long, thin strings of galaxies stretching between nodes. These are the highways of the universe, channeling matter from low-density regions toward high-density ones. A typical filament might stretch 160 to 260 million light-years. One of the longest known filaments identified so far, called Quipu, extends about 400 megaparsecs, roughly 1.3 billion light-years. That's larger than the distance between our galaxy and the nearest major galaxy cluster. Here's what's remarkable about filaments. According to cosmological simulations, they contain a large fraction of the universe's ordinary matter, with vast amounts of gas flowing along these structures. Not the voids, not the clusters, not the walls, the filaments. These thin threads, stretching across millions of light-years, are where much of the universe's mass resides. Think about that. The majority of everything that exists is arranged in strings. Filaments aren't just passageways for matter, they're active environments that shape the galaxies within them. Gas flows along filaments toward clusters, feeding star formation. Dark matter accumulates along their lengths, creating gravitational channels. Galaxies caught in filaments tend to have their spin axes aligned with the filament direction, as if they've been spun up by the flow. Then there are the walls. Walls are flattened, sheet-like structures that form where filaments merge together. They mark the boundaries between voids, the edges of emptiness. The most famous example is the Sloan Great Wall, discovered in 2003, which stretches about 1.37 billion light-years across, making it one of the largest coherent structures ever mapped. Walls contain superclusters and long chains of galaxy clusters. Laniakea itself is associated with a wall-like structure in our region of the universe. Walls are like the surfaces of the cosmic sponge, thin layers separating the inside from the outside. Finally, there are the voids. If nodes, filaments, and walls are where the matter is, voids are where it isn't. Voids are the dominant feature of the cosmic web by volume. Roughly 80% of the universe's volume consists of these low-density regions. These are regions where the density of matter is about 1/10 the average. Not completely empty, but spectacularly underpopulated compared to the rest of the cosmos. A typical void might span 30 to 300 million light-years. Within that volume, you might find a handful of galaxies, often dwarf galaxies, blue and actively forming stars, evolving in isolation, puzzling features in all of astronomy. But for now, here's the key insight. The cosmic web isn't a metaphor. It's not just a convenient way of describing the universe, it's the actual architecture of reality. Every galaxy you can see, every cluster, every supercluster exists because of its position within this web. And here's something that stopped scientists in their tracks when they first noticed it. The cosmic web looks like a brain. The filaments and nodes of the cosmic web bear a striking resemblance to the neurons and synapses of the human brain. The statistical properties of the two networks, the distribution of connections, the clustering patterns, the hierarchy of structures, are remarkably similar. Scientists have also found that the cosmic web resembles the network structure of the Internet, the root systems of forests, and even the foraging patterns of slime mold. In fact, researchers have actually used slime mold to map the cosmic web. Here's how it works. Slime mold, when spread across a surface with food sources scattered on it, will grow a network of tendrils connecting the food sources in the most efficient way possible. The organism optimizes its network for nutrient transport, creating pathways that minimize distance while maximizing coverage. Astronomers realized that the same optimization principles might apply to the cosmic web. They fed a slime mold simulation with the positions of 37,000 galaxies from the Sloan Digital Sky Survey, treating galaxies as food sources. The algorithm then grew a network connecting them. The result matched the cosmic web with remarkable accuracy. The same mathematical principles that govern a brainless organism's foraging behavior also govern the distribution of matter across the universe. Gravity, it turns out, is an optimizer too, pulling matter together in the most efficient configuration, creating a web that resembles the networks of biology and technology. This raises a profound question. Why do all these networks look the same? Is there some universal principle of organization that transcends scale, that applies equally to neurons in your brain, filaments in the cosmos, and tendrils of slime mold? Or is this just a coincidence, a pattern that emerges whenever networks form under certain conditions? We don't know yet, but here's what we do know. Within this web, there are structures so large they shouldn't exist at all. The universe has rules. One of the most fundamental is called the cosmological principle. It states that, on sufficiently large scales, the universe should look the same in every direction. No special places, no special directions, just a smooth, uniform distribution of matter averaging out all the lumps and clumps into a cosmic homogeneity. This principle isn't just philosophical. It's built into the mathematics of cosmology. The equations that describe the expansion of the universe, the formation of structure, the behavior of dark energy, they all assume the cosmological principle is true. And for the most part, it seems to be. Look at the cosmic microwave background, the oldest light in the universe, released just 380,000 years after the Big Bang. It's almost perfectly uniform. The temperature variations are only 1 part in 100,000. On the largest scales, the early universe was smooth. Based on how long the universe has existed and how fast structures can form, cosmologists estimated that coherent structures should not exceed scales of around 1 billion light-years, based on standard assumptions about structure formation. Anything larger shouldn't have had time to form since the Big Bang. The universe isn't old enough. And yet, in 2003, astronomers discovered the Sloan Great Wall, a wall of galaxies stretching 1.37 billion light-years across. It was the largest structure ever mapped at the time, and it exceeded the theoretical limit. Scientists debated whether it was truly a single structure or just a chance alignment of separate features. The controversy pushed observers to look harder, to map larger volumes, to see if other giant structures existed. They found them. In 2013, a team led by astronomer Roger Close announced the discovery of the Huge Large Quasar Group, a collection of 73 quasars clustered together across a region 4 billion light-years wide. Quasars are the brilliant cores of extremely distant galaxies, powered by supermassive black holes devouring matter. Finding 73 of them clustered in one area suggested the presence of a massive underlying structure. The huge LQG was more than 3 times the theoretical maximum size. "This is significant," Close said at the time, "not just because of its size, but because it also challenges the cosmological principle." Then came the Giant Arc. First reported in 2021 by astronomer Alexia Lopez while she was still a doctoral student, the Giant Arc is a crescent-shaped arrangement of galaxies, galaxy clusters, and gas spanning 3.3 billion light-years. It's curved, like a section of a gigantic cosmic circle, and it sits about 9.2 billion light-years away from Earth. The Giant Arc spans roughly 1/15 of the observable universe's radius, far larger than many models expect. It would take light 3.3 billion years to travel from one end to the other, Lopez explained. And it's just not supposed to be there. But all of these structures pale in comparison to the giant discovered in November 2013. It's called the Hercules Corona Borealis Great Wall. And if it exists, it could be the largest thing in the known universe. But its very existence remains hotly debated. The discovery came from an unexpected direction: gamma-ray bursts. These are the most powerful explosions in the universe, released when massive stars collapse into black holes or when neutron stars collide. A single gamma-ray burst can outshine an entire galaxy for a few seconds. Because they're so bright, they can be detected across vast distances, serving as cosmic beacons marking the locations of massive star formation. A team of Hungarian and American astronomers, led by István Horváth, John Hakkila, and Zsolt Bagoli, were analyzing data from the Swift Gamma-Ray Burst mission. They noticed something strange. In one region of the sky, centered on the constellations Hercules and Corona Borealis, there was an unusually high concentration of gamma-ray bursts, all at roughly the same distance from Earth, about 10 billion light-years away. When they calculated the physical size of this concentration, the number was staggering: 10 billion light-years across. That's more than 10% of the diameter of the entire observable universe. Light would need 10 billion years, nearly the entire age of the cosmos, just to cross from one side to the other. Hakkila has noted the structure would be too big to exist under many expectations. One reason the claim remains debated. The discovery sent shockwaves through the cosmological community. Some scientists accepted the structure as real, arguing that we simply don't understand large-scale structure formation as well as we thought. Others were skeptical, pointing out that gamma-ray burst surveys might have biases that create the illusion of clustering where none exists. A 2020 analysis by a different team found the evidence doubtful at best, suggesting the apparent structure might be a statistical artifact. But in the same year, the original discoverers published new analysis supporting their findings, using improved data and more rigorous statistical tests. Then in 2025, new research pushed the boundaries even further. Using updated gamma-ray burst catalogs, astronomers found evidence that the candidate structure may span a wider redshift range than previously thought, suggesting it could be even larger than the original 10 billion light-year estimate, though the true extent remains debated. Even more surprisingly, parts of the structure appear to be closer to Earth than previous measurements indicated. Since the most distant extent of the structure is hard to verify, the most interesting finding is that the closest parts lie closer to us than had previously been identified, explained John Hakala. If confirmed, this structure would represent a significant challenge to our understanding of cosmic structure formation, far larger than anything our standard models typically expect. So what does this mean? Either the Hercules Corona Borealis Great Wall is an illusion, a trick of incomplete data and statistical noise, or our understanding of the universe needs revision. The cosmological principle might be wrong, at least in its strong form. Perhaps the universe is lumpier on large scales than we assumed. Perhaps there are patterns we haven't accounted for. Perhaps the very foundations of modern cosmology need updating. A proposed mission concept called Theseus, currently under study by ESA as one of 3 candidate missions, could help settle the question if selected. With its wide field of view and improved sensitivity, Theseus would detect thousands of new gamma-ray bursts, especially from very distant sources. If the Great Wall is real, such a mission would map its full extent. If it's an artifact, the data would reveal that too. Until then, the question remains open. But here's what we know for certain. The universe contains structures far larger than we expected. The Sloan Great Wall, the huge LQG, the giant arc, possibly the Hercules Corona Borealis Great Wall. These aren't random fluctuations, they're organized patterns spanning billions of light years. The cosmic web is more complex than we imagined. And if the largest things in the universe are stranger than we thought, so are the emptiest places. We've talked about where the matter is. Now, let's talk about where it isn't. Voids are the dominant feature of the universe by volume. While galaxies and clusters and filaments get all the attention, they occupy only about 20% of space. The other 80% is void, vast, nearly empty regions where the density of matter is a fraction of the cosmic average. Think about that proportion. For every cubic megaparsec of space filled with galaxies, 4 cubic megaparsecs contain almost nothing. The universe is mostly emptiness. Voids aren't completely empty. They contain some matter, about 1/10 the average density. Scattered within them, you'll find lonely galaxies, often dwarf galaxies, blue with active star formation, evolving in splendid isolation. But compared to the bustling activity of filaments and clusters, voids are deserts. Cosmic wastelands where almost nothing happens. One of the most significant nearby voids lies in our own backyard. It's called the local void, and it sits right at the edge of our local group. About 150 million light-years across, the local void is so empty that the Milky Way and all our neighboring galaxies are actually moving away from it, being pushed outward by the relative lack of gravitational pull. One lonely dwarf galaxy, ESO 461-36, has been detected traveling through the local void at 135 miles per second, like a tumbleweed blowing across a desert. It appears to be heading toward more populated regions, fleeing the emptiness. But the local void is small compared to what lies beyond. In 1981, astronomer Robert Kirshner and his team were conducting a redshift survey, measuring how fast galaxies are moving away from us to estimate their distances. They expected to find galaxies distributed more or less evenly across the sky. Instead, they found a hole. At about 700 million light-years from Earth, in the direction of the constellation Boötes, there was almost nothing. A spherical region spanning 330 million light-years across contained barely any galaxies at all. At first they called it the Great Nothing. Later it became known as the Boötes Void. To understand how strange this is, consider the numbers. Based on the average distribution of galaxies in the universe, a region 330 million light-years across should contain approximately 2,000 galaxies. The Boötes Void contains about 60. Imagine expecting 2,000 people at a stadium and finding only 60. That's the Boötes Void. The void is so empty that astronomer Greg Aldering offered this thought experiment. If the Milky Way had been in the center of the Boötes Void, we wouldn't have known there were other galaxies until the 1960s. Think about what that means. The first photograph of another galaxy was taken in the 1880s. Edwin Hubble proved that galaxies were separate island universes in 1924. The entire history of extragalactic astronomy happened because we live in a relatively populated region of the cosmic web. If our galaxy had formed in the Boötes Void, our night sky would show only the stars of the Milky Way, surrounded by seemingly infinite darkness. Early telescopes wouldn't have revealed anything beyond our galaxy. We would have assumed, reasonably, that the Milky Way was all there was. Only with the development of much more powerful instruments in the mid-20th century would astronomers have begun detecting the faint, distant smudges that turned out to be other galaxies. And by then, our entire scientific and philosophical framework would have developed around the assumption that we were alone. The accident of our cosmic location shaped everything we know about the universe. Scientists believe the Boötes Void formed through the merger of smaller voids over billions of years. As the universe evolved, regions slightly less dense than average lost matter to denser regions, becoming emptier. Eventually, multiple underdense regions merged into the supervoid we observe today. But the Boötes Void isn't the largest void we've found. In 2015, astronomers announced the possible discovery of the Eridanus supervoid, a vast underdense region about 1.8 billion light-years across, located roughly 6 to 10 billion light-years from Earth in the direction of the constellation Eridanus. The Eridanus supervoid was proposed to explain one of cosmology's minor mysteries, the CMB cold spot. When you look at the cosmic microwave background, that ancient light from 380,000 years after the Big Bang, there's a region in the southern sky where the temperature is slightly colder than average. It's only about 70 microkelvins cooler, barely detectable, but it's there, and it's unusually large. One possible explanation is that between us and that patch of sky lies an enormous void. When photons from the early universe travel through a void, they lose a tiny bit of energy, stretched slightly by the changing gravitational environment. A sufficiently large void could cause exactly the temperature dip we observe. The Eridanus supervoid is a candidate explanation, but this remains controversial. Some analyses support the void's existence. Others suggest it's not large enough or not empty enough to explain the cold spot. The mystery persists. What voids tell us, regardless of their specific properties, is that the universe is fundamentally uneven. Matter clusters here, empties out there, creating a vast three-dimensional pattern of density variations. And here's something remarkable. Voids aren't just empty space, they're laboratories. Galaxies that form in voids evolve differently than those in denser environments. Without nearby neighbors to gravitationally harass them, without hot cluster gas to strip away their fuel, void galaxies keep forming stars longer. They tend to be bluer, younger-looking, and less disturbed than their cluster counterparts. Voids are also ideal places to study dark energy, the mysterious force accelerating the universe's expansion. In dense regions, gravity counteracts dark energy. In voids, with less matter around, dark energy dominates. By comparing the expansion rate inside voids to the rate in denser regions, scientists can probe dark energy's properties. And voids are perfect for studying neutrinos, the ghostly particles that barely interact with matter. Neutrinos stream freely through the universe, unimpeded by the gas and dust that affect light. Within voids, with less intervening material, neutrinos can be studied more cleanly. The emptiest places in the universe turn out to be some of the most scientifically valuable. Where did all this structure come from? The answer takes us back to the beginning, not just to the Big Bang, but to the tiniest fractions of a second after it. In the first moments of the universe, everything was hot, dense, and nearly uniform. But nearly is the key word. The early universe wasn't perfectly smooth. There were tiny variations in density, regions where matter was slightly more concentrated than average, and regions where it was slightly less. These variations were minuscule. We're talking about differences of 1 part in 100,000. If the average density was represented by the number 100,000, some regions had a density of 100,001, and others had 99,999. Barely detectable. But where did even these tiny differences come from? The best answer we have involves quantum mechanics. During inflation, that brief period of exponential expansion in the first trillionth of a second, the universe grew so fast that quantum fluctuations, normally confined to subatomic scales, were stretched to astronomical sizes. Random quantum jiggles became variations in the density of matter across millions of light-years. These quantum seeds were the beginning of everything. After inflation ended, the universe continued expanding and cooling, but now gravity had something to work with. Regions that were slightly denser had slightly more gravitational pull. They attracted matter from their surroundings, becoming denser still. Regions that started underdense lost matter to their neighbors, becoming emptier. This is gravitational instability. It's the mechanism by which small differences become large structures. But there's a crucial detail. The first thing to collapse wasn't the ordinary matter we're made of. It was dark matter. Dark matter doesn't interact with light, it doesn't collide with atoms, it just feels gravity and exerts gravity. This means dark matter could start clumping together while ordinary matter, protons, electrons, the stuff of stars and planets, was still trapped in the hot plasma of the early universe, unable to condense. Dark matter built the scaffolding first. By the time the universe was about 380,000 years old, ordinary matter had cooled enough to form neutral atoms. Light finally decoupled from matter, streaming freely across space. That's the cosmic microwave background we observe today. And now ordinary matter could feel gravity without being pushed around by photons. It fell into the gravitational wells that dark matter had already prepared. Gas flowed along the channels dark matter had carved, collecting in the densest regions, forming the first stars and galaxies. The cosmic web began to take shape. Here's the timeline. About 1 billion years after the Big Bang, the first galaxies had formed. Small, irregular collections of stars huddling in dark matter halos. These proto-galaxies were scattered along the emerging filaments of the cosmic web, clustered at the nodes where filaments met. By 3 billion years after the Big Bang, the web was clearly established. Galaxy clusters had grown at the nodes. Filaments stretched between them. Voids had expanded as matter drained away. The basic architecture was in place. Over the next several billion years, the web continued to refine itself. Filaments became thinner as matter flowed toward nodes. Voids expanded as dark energy accelerated the stretching of space. Smaller structures merged into larger ones. Galaxy clusters grew through collisions and accretion. Today, about 13.8 billion years after the Big Bang, the cosmic web has reached something like its mature form. Though it continues to evolve and will keep changing for billions of years to come. How do we know all this? We can't directly observe the web forming. It happened billions of years ago, but we can simulate it. Over the past few decades, astronomers have developed increasingly sophisticated computer simulations of cosmic structure formation. These simulations start with the conditions we measure in the cosmic microwave background: the density variations, the composition of matter, the expansion rate, and then run the laws of physics forward in time. The results are stunning. The Millennium TNG simulation, one of the most advanced ever run, follows billions of particles of dark matter and ordinary matter as they interact gravitationally over 13.8 billion years. It produces a cosmic web that looks remarkably like the one we observe: filaments, nodes, walls, and voids distributed in the same statistical patterns we see in galaxy surveys. This agreement is powerful evidence that we understand the basic physics of structure formation. Dark matter plus gravity plus the initial conditions from inflation gives us the cosmic web. The math works. But simulations have also revealed subtleties we didn't expect. For instance, researchers using Millennium TNG discovered that the longest cosmic filaments evolve differently from average ones. In high-density regions, filaments tend to collapse and shorten over time. Near voids, they expand and stretch as space expands around them. The web isn't uniform. Its properties depend on environment. Simulations also showed that the properties of filaments haven't changed much in the last several billion years. Most of the structural evolution happened earlier, when the universe was denser and gravity had more to work with. Today, with dark energy dominating, the web is more or less frozen in place. But here's what makes this story personal. The cosmic web isn't just the backdrop for galaxies. It's the reason galaxies exist. It's the reason stars exist. It's the reason you exist. Without the initial quantum fluctuations, matter would have stayed uniform. Without dark matter building the scaffolding, ordinary matter wouldn't have known where to collect. Without the filaments channeling gas, galaxies wouldn't have fuel to form stars. Without the clusters forging heavy elements through stellar explosions, there would be no carbon, no oxygen, no planets, no life. Every atom in your body was once part of the cosmic web's flow. Where a galaxy lives determines what kind of galaxy it becomes. This is one of the most important discoveries of modern astronomy. Galaxies aren't just passive participants in the cosmic web, they're shaped by it, transformed by it, sometimes destroyed by it. The web is an environment, and like any environment, it imposes selection pressures on its inhabitants. Let's start with the extremes. Galaxies in cluster cores. The densest nodes of the cosmic web tend to be red, old, and dead. They're elliptical in shape, smooth and featureless, containing stars that formed billions of years ago and nothing new since. Their gas has been stripped away. Their star formation has been quenched. They drift through the hot plasma that fills cluster cores like fossils suspended in amber. Why are cluster galaxies so lifeless? Multiple mechanisms contribute to their decline. First, there's ram pressure stripping. As a galaxy moves through the hot gas that pervades cluster centers, that gas acts like a wind, pushing on the galaxy's own cooler gas and ripping it away. A galaxy entering a cluster can lose its entire gas reservoir in a few 100 million years, cosmically speaking, almost instantly. Without gas, you can't make new stars. Star formation stops. The existing stars age and redden. The galaxy becomes a ghost of its former self. Second, there's strangulation. Even if a galaxy doesn't pass through the cluster core, its gas supply can be cut off. Galaxies normally accrete fresh gas from their surroundings, feeding ongoing star formation. But in cluster environments, this accretion is suppressed. The galaxy slowly uses up its existing gas with no way to replenish it. It starves to death over a few billion years. Third, there's harassment. In dense environments, galaxies frequently pass close to each other. Each close encounter exerts gravitational tides that disturb the galaxy's structures, strip away outlying stars and gas, and trigger bursts of star formation that consume fuel faster than normal. Repeated harassment transforms spiral galaxies into disordered blobs. Galaxies in voids face the opposite situation. Void galaxies are typically blue, young-looking and actively forming stars. Without nearby neighbors to disturb them, they evolve in peace. Without cluster gas to strip their fuel, they keep their supplies. Without harassment to disrupt their structures, they maintain spiral arms and organized rotation. Void galaxies are what galaxies would be if left alone. They're also rare. Because voids are underdense by definition, they don't contain many galaxies. The ones they do contain tend to be smaller than average, dwarf galaxies that never grew large due to the lack of material. But the most interesting environments might be the filaments. Filaments are transition zones. They're denser than voids but less extreme than cluster cores. Galaxies in filaments experience intermediate conditions, some environmental pressure but not overwhelming amounts. Research over the past decade has revealed that filaments have their own distinctive effects on galaxies. Scientists have found that galaxies within about 1 megaparsec of a filament's central axis show different properties than galaxies farther away. Closer to the filament, redder colors, lower star formation rates, more elliptical shapes. Farther from the filament, bluer colors, higher star formation rates, more spiral shapes. The filament is pre-processing its galaxies, starting the transformation from active spirals to passive ellipticals before they even reach a cluster. Gas flows along filaments toward nodes, and galaxies caught in this flow experience a kind of headwind that strips away their outermost gas. The effect isn't as dramatic as cluster ram pressure stripping, but over billions of years, it accumulates. What about our own galaxy? The Milky Way sits in a relatively quiet neighborhood. We're on the outskirts of Laniakea, in a small group rather than a massive cluster. Our nearest large neighbor, Andromeda, is far enough away that we don't interact strongly, at least not yet. This position may be significant for life. In cluster cores, with constant gravitational harassment and intense radiation from billions of closely packed stars, conditions would be harsh for planets. Orbits might be destabilized, atmospheres might be stripped. Life, if it formed, might be repeatedly reset by cosmic catastrophes. In voids, while conditions are calm, the building blocks for life might be scarce. Heavy elements, carbon, oxygen, iron, are forged in stars and distributed through stellar explosions. Void galaxies, with fewer stars and less star formation, might have lower abundances of these elements. Filaments and moderate density environments might be the sweet spot. Enough material to build planets, enough calm to let life develop, enough time for complexity to emerge. The Milky Way's position in the cosmic web, neither in a cluster core nor in a void, fed by local filaments but not overwhelmed by them, might be one reason Earth exists. We're in a neighborhood where life has a chance. The cosmic web is changing. Right now, as you watch this, dark energy is accelerating the expansion of the universe. Space itself is stretching, carrying galaxies apart, thinning the filaments, expanding the voids. The web that took billions of years to form is slowly being torn apart. What happens next depends on timescales. In the near term, meaning the next few billion years, local structure will continue to develop. The Milky Way and Andromeda are approaching each other at 400,000 kilometers per hour. In about 4.5 billion years, they may collide, though, as mentioned earlier, recent research suggests this is far from certain. If they do merge, the process will take about 1 billion years, resulting in a single giant elliptical galaxy, sometimes called Milkomeda. Galaxy mergers are not unusual. The Milky Way has already absorbed dozens of smaller galaxies over its history, and remnants of those ancient meals can still be detected in the motions of stars around us. The local group will likely consolidate over time. Its member galaxies may merge over tens of billions of years, potentially forming one enormous elliptical galaxy containing the combined mass of everything currently in our neighborhood. On larger scales, galaxy clusters will continue to grow by accreting matter from filaments. The densest clusters will become even denser. The nodes of the cosmic web will become brighter and more massive. But there's a limit. Dark energy is accelerating the expansion of space. Currently, nearby galaxies are still gravitationally bound to us. The local group, the Virgo cluster, even much of Laniakea. But galaxies beyond a certain distance are receding faster than light. They're beyond our cosmic horizon, forever out of reach. As dark energy pushes expansion faster and faster, that horizon shrinks. In about 100 billion years, observers in what was once the Milky Way will look up and see almost nothing. All the galaxies beyond our local cluster will have been carried over the cosmic horizon by expansion. The light from them will be so redshifted as to be undetectable. The cosmic microwave background will have stretched to wavelengths so long that no instrument could measure it. The filaments of the cosmic web will have been stretched to invisibility. The voids will have expanded to encompass everything. The grand structure we've been exploring, Laniakea, the Great Wall, the Boötes Void, will be gone, carried beyond the knowable universe by the relentless stretching of space. Future astronomers, assuming any exist, will see only their local cluster, a few dozen galaxies merging together, surrounded by what appears to be infinite emptiness. They will have no evidence that the universe was ever larger, no way to know that trillions of galaxies once blazed across the heavens, no cosmic microwave background to measure, no filaments to trace, no structure to map. The cosmic web will be erased. This presents a disturbing thought experiment. What if the same thing happened before us? What if the universe once contained structures or features that have already been carried beyond our horizon, erased from our observable cosmos? We would have no way of knowing. We live in a special time. It's a brief window in cosmic history, brief on cosmological scales, though it spans many billions of years, when the universe reveals its structure, when light from distant galaxies still reaches us, when the cosmic microwave background still carries information about the early universe, when the web is visible. This window opened a few billion years ago and will close 100 billion years from now. Compared to the potential lifetime of the cosmos, it's a fleeting moment. We happen to exist in that moment. Whether this is pure coincidence or something deeper is one of cosmology's most perplexing questions. The anthropic principle suggests that observers can only exist when conditions permit observation. But the implications of that idea are controversial and possibly untestable. What's certain is this: we are the first generation of intelligent beings, as far as we know, to map our position in the cosmic web, and we may be among the last generations to see the web at all. Every observation we make, every survey we conduct, every structure we map is a record for the future. We're documenting a universe that will eventually erase itself from view. Let's put together what we've learned. You began this journey thinking you knew where you were. Earth, orbiting the Sun orbiting the Milky Way. The Milky Way, one galaxy among many. All true, but incomplete. The Milky Way is one of more than 50 galaxies in the local group. The local group is part of the Virgo cluster's extended family. And all of this, everything within 500 million light-years, is part of Laniakea, the immense heaven, our home supercluster. Laniakea isn't floating in isolation. It's connected by filaments to neighboring superclusters: Shapley, Hercules, Perseus Pisces. These connections are part of the cosmic web, that vast three-dimensional network of matter stretching across the entire observable universe. Within this web, matter is organized hierarchically: nodes where filaments meet, filaments stretching between nodes, walls where filaments merge, voids where matter is sparse. The largest structures, the Sloan Great Wall, the huge LQG, possibly the Hercules Corona Borealis Great Wall, challenge our understanding of how structure can form. Everything you see in the night sky is part of this web, and the web shaped everything you are. The cosmic web determined where galaxies formed. Galaxy formation determined where stars could exist. Stellar evolution created the heavy elements that became planets. And somewhere in this vast cosmic architecture, on one unremarkable planet, orbiting one ordinary star in one typical galaxy, in one modest supercluster, beings made of stardust learned to look up and ask, "Where are we?" Here's your full cosmic address: Earth, Solar System, Orion Arm, Milky Way Galaxy, Local Group, Virgo Cluster Region, Laniakea Supercluster, Cosmic Web, Observable Universe. That's where you are. 9 levels of structure, each one larger than the last, each one revealing new patterns and new mysteries. From a rocky planet to a 93 billion light-year cosmos, connected at every scale by the same fundamental forces: gravity pulling matter together, dark energy pushing space apart, quantum fluctuations from the beginning of time setting the pattern for everything that followed. Some of what we've discussed remains uncertain. The Hercules Corona Borealis Great Wall might not exist. Dark energy might behave differently than we think. The cosmological principle might hold on scales we can't yet probe. Science is a process of revision, and our map of the cosmic web will continue to change. But the basic picture is solid. The universe has structure. That structure took billions of years to form, and we're embedded within it, shaped by it, made possible by it. There's one more thing worth reflecting on. Of all the places in the cosmic web where matter has condensed into galaxies and stars and planets, This particular place produced beings who could figure out where they are. The chances of this seem astronomically small. The universe is vast, 93 billion light-years of observable cosmos, trillions of galaxies, septillions of stars. Most of that volume is void. Most of the matter is in forms inhospitable to life. And yet here we are, on one rocky planet, mapping the entire structure. Some see this as evidence that the universe is fine-tuned for life, that the constants of nature, the initial conditions, the whole cosmic setup was somehow arranged to produce observers like us. This is the anthropic principle in its strong form, and it remains deeply controversial. Others see it as survivorship bias. Of course, we find ourselves in a place compatible with our existence. We couldn't exist anywhere else. There's no mystery, just logic. Still others see it as a challenge. Maybe life is more common than we think. Maybe other observers on other worlds, in other superclusters, are also mapping the cosmic web. Maybe intelligence is the universe's way of understanding itself, and we're just one of countless instances. We don't know which view is correct. We may never know. But we know this: the cosmic web exists, we're part of it, and we've learned to see it. That's extraordinary. There's something profound in knowing this. For most of human history, the night sky was a mystery. Lights in the darkness, unexplained and unexplainable. Now we know. Those lights are stars. The stars are in galaxies. The galaxies are in clusters. The clusters are in superclusters, and all of it is woven together in a web that spans the observable universe. We figured it out. Humans on this one tiny world mapped the cosmos. Not completely, not perfectly, but enough to know our address, enough to see the pattern, enough to glimpse the architecture of reality. There's a final thought that brings this journey full circle. We started by noting that you're not where you think you are. Your cosmic address is longer than you imagined, more complex, more connected to the rest of the universe. But here's what might be the most surprising realization. Your position in the cosmic web isn't random. It's the result of 13.8 billion years of gravitational choreography. Dark matter collapsing, gas flowing along filaments, galaxies forming at nodes, stars igniting and scattering heavy elements, one rocky planet condensing at just the right distance from one ordinary star in one typical galaxy. Every step of that process was necessary. Change any step and you don't exist. The next time you look up at the night sky, remember, you're not just seeing stars. You're seeing the threads of a web that stretches 93 billion light-years. You're seeing the light of galaxies that began their journey before Earth existed. You're seeing the structure that made your existence possible. And somewhere in that web, connected by filaments of dark matter and flowing rivers of galaxies, is a small blue world where beings made of stardust learn to ask the biggest questions of all. We are small, we are brief, but we are the part of the universe that knows it's a web. And maybe that's enough.